Hello class, this is going to be our flipped classroom on VSEPR theory, and VSEPR is a shorthand term for the words valence, shell, electron, pair, repulsion. So this video is all about shapes of molecules and how we can predict the shape of a molecule by knowing the bonding. And it works on one very simple theory, and that is that electrons, being negative, don't want to be next to each other. So if you create a molecule that has more than two atoms, the electrons on those atoms will push each other apart so they're as far apart as possible. And from this we can predict the shape. So here's what I'm going to show you. Let's start with the first type of molecule, which I'm going to label an AB2 type. Now what do I mean by an AB2? A stands for the central atom and B stands for the atoms that are attached to it. So in this example I have a 3-atom molecule, a central atom with 2 atoms attached to it. So for example, carbon dioxide, CO2, would be an AB2 molecule. So what will CO2 look like? Well, let's take a look here. And you can see that I drew CO2, and we've drawn this before in a previous video, with 2 double bonds and an oxygen on the left and on the right there. And the way I drew it was I drew them straight across from each other. Now, why didn't I draw it like this? Well, that's because according to VSEPR theory, these electrons that are on the oxygens want to be as far apart as possible. And right here, this is a 90-degree angle. I think I can do better because the bond angle between here and here is 180 degrees. That's the maximum I can get those 2 oxygens away from each other. So therefore, the name of the molecular geometry, or the shape of the molecule, is called linear, and it has a bond angle of 180 degrees. So now let's move on to another type of molecule. We'll call this an AB3 type. One with 1 central atom and 3 atoms attached to it. So for example, SO3. Now what does SO3 look like? Well, when I draw SO3, this is how it looks. First, using the octet rule, I know that I'm going to have a double bond between one of the oxygens and then 2 single bonds. Otherwise, I'm going to violate the octet rule. And as you can see, I've drawn it in this kind of like weird pattern. Why didn't I draw it more like this? Well, because the bond angle here would be 90, and here would be 90, and here would be 180. Why would I not make them all the same bond angle? After all, they all want to be equally far apart. So if you figure out the bond angle between OSO here, and OSO here, they're all the same. They're 120 degrees. Now, what do we call this shape? Well, if you connect these oxygens like this, what shape does that look like to you? You're right, it's a triangle. So the name of this shape is called trigonal planar. In other words, a flat triangle with 120-degree angles. Now let's do something weird. Let's make a molecule that has a central atom, A, 2 bonded atoms, 2 B's, B2, and on the A is a pair of electrons. So we'll call that E. So there is a lone pair of electrons on the A. An example would be SO2. So here is SO2. And you can see I drew it in this shape, kind of like this. Now, why didn't I draw it as a linear molecule, like this? Well, that's because these electrons on the sulfur are going to push the oxygen electrons away so that they're not next to each other. Or in other words, these pair of electrons take up space like there was a bond there, and they push away, not any different than SO3. So the bond angle is also approximately 120 degrees, because all of these are approximately 120 degrees. What do we call this shape? Well, we're not going to get fancy here. We're just going to call it bent, because it is a bent molecule as opposed to being a linear molecule. And the bond angle is somewhere around 120, probably a little bit less. Now the next molecule, AB4. Now if I were going to try to draw AB4 on paper, this is what it would look like. And I think you'd agree that in 2 dimensions, there is no way I can do better than drawing these 90-degree angles. However, remember, we don't live in a 2-dimensional world. We live in a 3-dimensional world, and the angles do not have to be 90 degrees. If I draw it in 3 dimensions, and again, I'm not very good, so take a look at this picture. There's my carbon, and there's an H, an H, an H, and then an H going backward into the paper. You can see that this bond angle and this bond angle and these angles are better than 90 degrees. As a matter of fact, they're approximately 109.5 degrees. So it actually doesn't look like a plus sign. It looks more like this shape, which is called a tetrahedral. So CH4 forms a tetrahedral molecule. That's the shape. Now let's take away one of those 4 B's. Let's keep 3 of them, but once again have a pair of electrons on the A. So we'll call this AB3E. An example of this would be ammonia. And take a look at the way ammonia looks. Again, on paper, I'm just kind of drawing it like a T shape. But again, if I consider that I'm starting with a tetrahedral, but then I'm removing this top one, what have I got left? Well, if I look at a picture of it, this is kind of what it looks like. It looks like it's a pyramid, but with a pair of electrons on top right there. So the name of this shape is called trigonal pyramidal. It's a triangular pyramid. And again, the bond angle is somewhere around 109.5, probably a little bit less, because free electrons tend to take up more space. The last type of molecule I want to show is a molecule which I'm going to label an AB2E2 molecule, which is a central atom, 2 B's attached to it, and then not 1 pair, but 2 pairs of electrons are on the A now. Water is an example of that. And what is the shape of water? Well, we've discussed this earlier. Water is bent. Now, why isn't water linear? Why doesn't water look like this? After all, isn't this as far apart as we can get the hydrogens and the electrons? In 2 dimensions, absolutely. If you're going to pretend that there's a bond here and here, this would be 90 degrees. You can't do better than that in 2 dimensions. But in 3 dimensions, remember, we're basing it off of the tetrahedral. It's like we're basing it off of CH4, but then we're removing a bond here and removing a bond here. Then how far apart are they going to be? Oh, wrong one. They're going to be, again, about 109.5 degrees from each other. In water, I believe it's closer to like 107. And the bond angle is 107 or 109-ish because the furthest apart you can get these atoms, including these pairs of electrons, is about 109 degrees. And again, the shape looks like this, so it is bent. The only thing I want to point out is that water's bent shape and SO2's bent shape are not the same angle. Water is based off of the tetrahedral, right? So water is not 120 degrees. Water is about 109.5 degrees. Like I said, probably closer to 107. But as you can see, it's not the same angle as SO2's bent, because SO2 was based off of an AB3 molecule, where water was based off of an AB4 molecule. And that is VSEPR theory.